Hello, everyone. Okay, so we're back. It's been a little while, like a week, but we're back now. And today, my plan is to try to see if I can get Tinygrad running on the Vector Engine. So, a technical stream. So for those who do not know, Tinygrad is a library that's made by Tiny Corp, which is founded by GeoHot, and it's small, and that's great because you get a lot of bang for the buck in terms of how much work it is to implement something. You can get a lot of out of it from implementing just a small amount of stuff, and that's good because we only have a small amount of time on these live streams, and so I don't want to spend too much time, on useless kind of specifics. It's mainly just to see what kind of performance I get or what kind of issues come up, and so on and so forth. So anyway, Tinygrad is pretty simple to port. If you look, it has a little section on adding new accelerators. And essentially, there's a few low-level ops that you have to implement, and then some ML ops that you have to implement, and then high-level ops. And yeah, if you just implement those, then that works. And if we look at what those look like, for example, on the CPU, he has implemented them in terms of NumPy, which is pretty simple. That's an interesting way to go about it. This is crazy annoying, the formatting here. But yeah, essentially you have an allocator of some sort, and then you create a something device, and then it will, or Tinygrad will, when it's initializing itself, as you can see here, it will try to find what devices it has access to and return the right one. Either if you specified it through an environment variable, or it'll just try to pick one that's not the CPU, and if it can't pick anything that's not the CPU, it'll just return the CPU. So that's Tinygrad for you. And I'm not sure Tinygrad is like super fast, or at least in the things that I've been playing around with today, it's not exactly super fast. But it's kind of like decent. But anyway, I have actually been getting it kind of running. So let's look at what I have been able to do so far. So this is my fork of Tinygrad. You can get it. Well, I haven't pushed anything yet, but the idea is I will. As a first try, I decided to implement NLCPy, because it's a NumPy wrapper. It's not a complete NumPy wrapper. There's a few differences, and that's where the bulk of the time is going to be. Yeah, but essentially, just implement the CPU device, change it to VE device like so. Deal with the fact that the VE doesn't support uint8, or it kind of does, but the NLCPy does not. So that's usually a good thing because bytes would go on the slow path, not the vectorized path. So kind of makes sense, but kind of relies on buffers and stuff like that. So this might not be the most efficient thing in the world. But, you know, it could work, right? Now, the ugliest thing is that einsum is not supported by NLC, so I have to deal with that. Anyway, so let's see where I'm at right now. So, for example, there are these examples in the repository, Tinygrad, and we can look at the beautiful MNIST example, which I'm not sure why it's called beautiful MNIST. I feel like I've seen better. Let's see, where is it? Examples, beautiful MNIST. It's not in data sets. There you go, beautiful MNIST. So I haven't changed too much in here. I've just been playing around with it. It should actually be the same kind of thing. But essentially, you have like this little model here. And you can see, if you know what PyTorch looks like, then you'll know what this looks like. That's pretty much the same kind of idea. You have your init where you define your layers, and then you override call. And yeah, it doesn't have to be an object like this. There's nothing special about it. It's just the way it's implemented here. So if you look, we fetch MNIST, we turn it into a bunch of tensors, create our model, and we create an optimizer, and then we train little by little and stuff like that. Apparently this is supposed to run in 5 seconds, but if you notice, there's this example here. This gather of samples is very slow. Will be under 5 seconds when this is fixed. And yeah, so it's crazy slow. I remember, I mean, 5 seconds isn't that fast. I think in my laptop with DL4j, like 3 years ago, I was training very similar things like this in like 3 seconds or something like that, 2 seconds. It's like, you know, essentially instant. But anyway, so given this beautiful MNIST, we can actually try running it. So if you run it like so VE equals 1, that would run it on the VE. If you want it on the CPU, do CPU equals 1. So right now, to just show where we're at, I'm going to try to make this a little bit bigger. And let me also move my face down there. And yeah, so some issues. We are currently doing, let me see what kind of issue I have here. Essentially, the thing I'm doing here is we create ops VE, and this mul ACC is where the bulk of the work is, right? And it relies heavily on einsum, which NLC does not support, which is strange. It seems to me like einsum is something that could be implemented in Python and then just wrapped. But anyway, I've kind of looked through and see which kernels are being implemented, and then transform those into NLC Pi calls. And this one is interesting because if you just do it this way, it's going to allocate 150 gigabytes of data, which is it's kind of a lot. And I have a bug in this one, so I'm just going to skip it for now. So this should be 57. So this one is not correct, so I'll just skip that one. Actually, maybe all of these are wrong. Can do it. But essentially what this method does is it matches on it, does the VP version, the vector engine version of it, and then if it doesn't work, it falls back to NumPy. And I think the first ones were actually pretty good. These last ones, not so much. Something is wrong with those. Could be that I have A and B mixed up. I'm not 100% sure how Einsum works. It's a little bit after my time. Okay, and yeah, let me just get rid of these ones. These top ones I'm pretty sure are correct. The bottom ones are a little iffy. And we can kind of see the different kernels that are being run and things like that. We can actually see the status of the vector engine here. So if I run this tload, we can kind of see where the vector engine is being used. And essentially when the CPU is like doing a lot of stuff, that's when we're using NumPy. And then when only a single thread is kind of at 100% or two threads are at 100%, that's when we're using the vector engine. Yeah, with this, we're running a few things on the CPU, but it is training. It's not training particularly fast, but at the moment, that's fine for our purposes. But anyway, that's kind of cool that it kind of works. But I think, you know, NLC Pi is not exactly the best way to implement all of these things. And yeah, like this is really relying on Einsum for everything, and it could be running like custom C++ things. I think. Right now, this might look pretty slow, but this is more or less what the CPU is at, so it's not incredibly slow or anything like that. That's just the way. It's just the way it is. Apparently, this thing is slow, right? And it's weird that it has to be slow like that. I'm not sure why this gather has to be slow. But yeah, it's training. It's using the vector engine somewhat. If we do VE top, we can kind of see different threads. It is. It's always going to say 100% here, so that doesn't really matter. You can see we're using 13 gigabytes of memory, or 13% of the memory. So what's that? 6 gigabytes. It's pretty normal. I think there's a big buffer that's like pre-allocated. So yeah, it's nice that Tinygrad is kind of simple in that way. So yeah, in this thing, I'm just going to keep implementing it, answering questions if you have any, and kind of see what we can do. There's a few interesting things that Tinygrad relies on, which required a little bit of monkey patching, not a serious amount. But apparently, they call this broadcast to with a none. So I had to implement this. It's a hack, I guess. Essentially, I didn't know, but if you do like NumPy as any array or something like that, it will fill it with nans and reshape. Or I think, yeah, if you do mp.broadcast2 and then you have a nan or an array with a nan in it, or none, it will create an array of nans. So I have to do that. This compare less than is not supported for uint8, so let's fix that. But I want to start from a place where things run, maybe not ideally or something like that, but a lot of the shapes are optimized to be uint8, which is unfortunate for the current way of doing things because they're kind of slow. So yeah, I'm just gonna you do this other way. So output type XY. I think I need to do something here. Let me do a compare less than function. I'll just call it with X and Y. That way it's kind of simple. Compare less than XY. And then we usually want to return this, but if X, if output type XY is equal to numpy.uint8, then I want to do like mp.asArray X less than mp.asArray Y as type XY. It's kind of dumb to write it that way. And then else I'll do it this way. So let's see how that works. But yeah, this is one thing that I wish I could deal with in a different level. I'm not 100% sure how to do that. As to why NLC Pi doesn't support uint8, well, we can go to our trusty wiki chip. So the way the vector engine kind of works, let's go to the SX Aurora microarchitecture here. So there's the scalar processing unit and the vector processing unit, and this thing only supports 32-bit or 64-bit floats, or 32-bit or 64-bit ints, both unsigned and unsigned ints. And yeah, if you have 128-bit floats or 8-bit floats or shorts or anything like that, that gets processed on the SPU, which is very slow. It's not, it's not unreasonably slow. It's just, it's like a 1.8 gigahertz processor, so it's not going to be super fast. And to avoid those kind of issues, the NLC people just decided to not support uint8 like that, which is fine. Not the end of the world there. But yeah, it means that we have to always do this kind of guard thing. So if we're dealing with uint8s, we do those in the CPU. And from my understanding, these are all shapes. So, to calculate the shapes of the output types and things like that, we're kind of using these bytes. Well, I guess they shouldn't really be shapes. Well, I know that some shapes are this, but having uint8 be the shapes is kind of weird. I think it's mainly used as some sort of buffer. I'm not 100% sure how that works. But we'll figure it out. And apparently, we are not, this did not work. Okay, I guess we'll have to do if.dtype is equal to mp.uint8 or y.dtype. Yeah. It's a little bit of a slog. But in general, this is this is the main thing, right? Like all of these are kind of like small things. Most of the stuff is multiply and accumulate. And yeah, it's quite complicated, this thing. Pretty much it takes the A axes and A slices and B axes and B slices. And then this small amount of code is doing a lot of heavy lifting, essentially, which is kind of amazing. So we'll see how this works. I would like to look at implementing this with a C kernel, which would be kind of cool. Luckily, NLC Pi makes that kind of easy. So if you look at NLC Pi, part of the NEC SDK, it has this feature for just-in-time compilation. So you can do custom VE library and then just create this code. Then you can get that function and run it, which is pretty cool. So we'll see if that's something that we can do, maybe with the help of a model, like an AI model, to make that be less of a slog. But I'd really like to get these things ported. But some of them, like this first one that I commented out here. The problem with this is the size is crazy. So this Einsum is optimized somehow to keep it from blowing up, which is kind of interesting. I don't know why this is BA here. CDGH, ADEF. Yeah, very interesting. I'm gonna have to look at how this Einsum is implemented in general. It's a pretty complicated but very small function. So it does, like I said, it's doing a lot of heavy lifting. Yeah, it is pretty nice, right? Like you need to see this kind of stuff. Like that's using the vector engine. Now it's switching to the CPU. And the more and more of the vector engine we can use, the more quickly it will run, because the PCI interface, the PCIe interface is kind of the bottleneck here for each one of these. Man, this is some terse code. One interesting thing is this LLVM version, which creates code. And then there's also the Clang version, which we could also possibly do something with. But I'm not sure right now how this works, like, to tell you the truth. This is a Clang device, which is a compiled device. But yeah, how that works, I'm not 100% sure. I'm not sure float 4 Is that a 32-bit float? If it's false, I'm assuming it's not. The CUDA one is involved, but not unreasonably so. The HIP one is also kind of interesting. Because it kind of has a more specific allocator here. And the metal one is also kind of interesting, especially because it's like hacked, right? Like they're kind of like reversed engineered how to use metal on the devices. Well, I'm not sure if he's. I remember watching on a live stream where he was trying to reverse engineer how the neural engine works. I'm not sure if he's doing any of that here, but with metal, he can at least get to the GPU and sometimes to the neural engine as well. And then the torch one is pretty simple. It's just calling torch for those, and torch einsum. So yeah, this is the main thing where stuff gets done, and it's gonna be a little long. Where does this device come from? I see. So this is a way to use CUDA or MPS. And Web GPU, this is also really interesting. I didn't know he had this. And I wonder how it works. There's an example, and I looked at it, and I don't understand. Because I don't see how to compile it. Yeah, I'm kind of wondering about this. Really wondering about this Clang. Because I notice it's not in the options, right? So I'm not sure how these compiled devices work. If someone knows, you can let me know. Wait, the docs say that mul ACC is optional? I gotta try that. Wait a second. So if I go to ops VE, I gotta figure out how that Clang one works. I definitely want to try it. And we do not do that. What happens? It's mostly on the vector engine here. And it's out of memory. Okay. So while it might be optional, it might not be ideal. DP multiply. Wait, did it really use that much memory? Because that's, 48 gigabytes, that's a lot of memory, It is kind of using a lot of memory, that's true. Yeah, on the vector engine it's not using it, but on the host it's kind of doing a crap ton of memory. We are at from data. Yeah, let's look at this real quick. Match types X, Y. Let me implement different match types that prints out X dot shape. Let's do something like this. Shape is X shape. X dot D type is X dot D type. Y dot shape. Then Y dot D type. Okay, so let's see what's kind of going on under the hood here. Why that's so huge. That's not that big. I wonder. That's weird. If I do the simple, so I also have a VE test, which runs. Looks very wrong. Yeah, it's definitely wrong. And if I turn that on, that wasn't wrong a little while ago. Let me also run this with no rep. That makes a lot more things. Tensor dot is not implemented. That explains some things. I thought I had that turned on. Okay, so man, if tensor dot isn't implemented, that kind of removes a lot of pretty much everything here. Buffer is allocated. What did I get wrong? Okay, let's do that. Okay, so that's better, I think. Train efficient net. We don't want to do that. I want Python VE test. That's still very, very wrong. Let's get rid of the INSUM here. Let me check. Is this like, so we need to check, is this uninitialized memory or something else? So we'll check the VE test here. Let's change these to 42 and negative 42. And try that and see if they are different values. They might not be. That's interesting. Okay, print X. If that's working. That does not look like an I at all. does that work? Yeah, so that's how it should look. And it does not look like that right now, which is weird because it was kind of looking like that a little while ago. So shapes are okay. Doesn't have anything to do with this monkey patch, I don't think. Yeah, doesn't have anything to do with that, so get rid of that. And yeah, let's just double check. We should get an I, and then the 2s and the 1. What we get instead is very off. What if I redo this? Okay, so let's copy the Tinygrad runtime. Let's move ops ve.py to no ops .py, and then copy ops cpu.py to ops. Okay, from there, we have this. We need to call this VE device, and then we should be mostly good to go. And what happens if we do not implement that and run it like this? Examples. Okay, so that is working and is okay. And we can also run the beautiful mist, and that works. But because it doesn't have einsum, it might be incredibly slow, or oh no, using up all the memory in the entire CPU is the way that works. Makes sense. Why does that need 90 gigabytes of memory? $90 gigabytes of memory for 60,000? That's really weird. Let's see, how do we run? So Trio has a good idea of running things synchronously. I do not know how to do that. So let me see how to do that. Is there input, output? I remember there was something like that. range, finite variables, the node list, mem size, num threads. One sec. Sorry about that. The kids like to come into my room. Oh, wow, that's interesting. Sorry, statistics. What was the synchronous thing? Flushes the requests to the VE. Is it this VP request flush? I thought there was like a synchronous mode. They might have changed it. The last time I looked at this was at 2. Like in the 2.3 timeline. VE node synchronous. Guess we can call that. Yeah, there was like a thing that you could call back in the day to make it always synchronous. Synchronize all VE is one way of doing it. I can't remember how to do. We could do things little by little now. So, for example, if we do import LC pi as VP, let's see, set offload timing on the fly. Aha. Okay, yeah, let's try this. So we'll do that, then all that node 0. VP request set offload timing on the fly. Okay, now our alloc can be if alloc has to be that. Then as buffer, I think has to be like that. And then our copy in and copy out are like this. Yeah, sorry if you see the door opening and closing all the time. For some reason, they see me doing something and then they leave and then they forget that I'm doing something. Okay, let's try. Let's just see what happens if we turn on the syncing on the fly thing here. And the no ops VE, like so. Then we move the Tinygrad runtime. No ops VE. to Tinygrad anytime speed of pi. There we go. And then if we run a VE test, we need a VE node. And to get the VE node, we need to do VE node 0. I think that should do it. Okay, here we go. VP dot node 0. And it takes 4, but we have 1, so we need that's what we want. There we go. Yeah, it doesn't seem like that. That's what it is. Okay, so let's go back to. So let's move that back to that, and then move aux CPU, aux VE, and we'll import NLC Pi as VP, and let's reinstate this just so that we know for sure that things aren't weird. Okay, and then in here, I think we can copy this part. And that should be fine. If we run this, it will fail, but that makes sense. So it fails in specifically the allocator. The reason why I think it's like the synchronizing kind of works is because Tinygrad is also asynchronous, so I would expect it to kind of work. But at the same time, we don't have like a synchronous call anywhere, so or like a sync method to implement or anything like that. So well, let me check the GPU real quick. Did this have a? So I can see let's put a CUDA. I got CUDA program. Interesting, it has a free here. So there is a synchronize. The device. This is a compiled device. So if we have a non-compiled device, okay, so ops VE Pi. Let's create a device. Do we have an interpreted device? We do not. all compiled. Hmm. I wish I can figure out where this is. Okay, so maybe interpreted doesn't have a doesn't have the thing that we want. I'm just working with a real IDE. Synchronize. So compile has synchronized. Interpreted also has synchronized. Okay. So let's look at that. Let's do ops VE. VE device is an interpreted. And this takes some. Doesn't take anything, and then what we want is super self.init. NumPy allocator, and then NumPy functions for op. And we'll do our def synchronize, which we look back at here. We do the thing. So from the NLC Pi perspective, synchronize is synchronize all VE. I think we just call that, even though we only have one VE at the moment. Okay, now if we run the VE test, buffer object is now allocated. All right, that was the same issue that we had before. CPU function buffer down. Module name ops CPU. Did I? Oh, I moved it. That would work. Check out. Let's restore that. Okay, so that actually ran. Let's just double check that it actually runs. It never does. Okay, so kind of do it that way. Interpreted. Interpreted, which is here, takes an allocator and a function. Am I not passing those two things? Check. Were there any other interrupted? Let's go back to ops CPU. If I just do it that way. Okay, so this is an instance. Okay, these are classes. They just take a device. Okay, I think we can work with that. So the class is this. It takes in itself and device, and whatever it is that it gets. And one must be a type, not a VE device. Where is that coming from? Let's probably do this correctly. Was that necessary? Okay. Can we just do that now? Yes, we can. Python. Okay, we're still getting really weird results. We enable the wrap. Still the thing, yeah, so that makes no difference. We have our allocators happening here. Let's see. Unit to as a file buffer. I don't think Python. Let's import NLC Pi and see if NLC Pi has a firm buffer. It does. So don't need to do these shenanigans. Well, we'll see. And from buffer is not implemented yet. But if the wrap is turned on, then it runs. Use test outside. Should be copying to yeah, that's what I was thinking when I looked at it. It was like that. It's allocating something. Copy in. So we need to take dest and MP from buffer. And here, is this what it was supposed to be like? Let's double check that. CPU implementation. Copy to numpy from buffer dest reshapes. So here we have UP from buffer reshapes the source, which maybe doesn't have to be on the VE per se. What's this roux shape? What that? That was never called. Are these ever called? Only this one is. Turn off wrapping. If from buffer is not implemented yet, so this is a problem. That's a Python thing. So we want to copy this to dest. Do it that way. Must be an NLC pi MD array to copy to that dest. The problem with this is it's like owning the arrays. If we do this, then we're just left with NumPy arrays. So if we go from here and start running a training, it just runs because it's pretty much all in here. No, I guess not. There's no required. As buffer. Let's look at the metal or the GPU. So the allocator here creates the buffer. And what this returns is totally up to it, at least in the compiler. Let's go here. So second LBP. Okay. Fire is not implemented yet, which we get from here. And that's fine. This get essentially returns the NumPy version, right? So like, you just do this, then now we're in NumPy land. Which should work, right? Yeah. What's it doing on the vector engine? Not copying anything. It could be that this is NLC Pi just waiting to give instructions to the vector engine. Okay, so let's make a different allocator. Now the problem is, ideally, what we want here is a VP empty, but the D type is the problem. That is the problem. Essentially, what this is like low-level allocate. It's just saying I need these bytes. By saying MP empty, it's reserving that amount of space, and then after that, it's casting that to whatever it wants. So that is interesting. I'm not sure how to do the same thing. Let's do float 32, which is 4 bytes. So therefore, we need to do VP size divided by 4. Does that work? Who knows? Let's flat MV. Flat MV is here. GPU does not use that flat MV. Yeah, it does not. Okay, so maybe we don't need that either. So as buffer, is there, what happens if we just run like this? I don't want to see what error we get. NumPy allocator is not defined because I named this NLC Pi allocator. Okay, and then that's fine. That's fine for me. Okay, so we have our allocator, and it's returning this as buffer, which self.allocator free. We might need to implement a free, which I did see in the other thing. So if you look at the ops GPU is alloc, and then underscore free. So if we just implement that with a no op, we have our buff the something. What is calling this? Self.buff is a Tinygrad device.pi. Self.buff is the buffer as the allocator. And then del buffer begin use something that we call allocator copy in. We have from CPU and to CPU, which is interesting. From CPU and to CPU. I see. Oh, this is calling as buffer. So if it does have as buffer, it returns a numpy empty and then copies. Okay, so we can do that. So let's get rid of this as buffer. We don't need it. It's done. Well, maybe it's not that done. But we have our copy in and our copy out. Let's copy in. Copy in. Takes that. The source is a memory view, and the source is just whatever we copy out. So if this is just a numpy.nd array, and then this source is an numpy.nd array, I don't know if that will work. So we want to copy into VP, and then just copy to as array. That might work. And then the flip side. Yeah, that's what I'm wondering right now. Like, so it will use copy in and copy out from here. So from CPU makes a buffer, and then it copies in. And then to CPU turns the ND array. And if we do the wrapping, that would all be automatic. So the only thing we have to deal with is this uint8, right? So if it is a uint8, we just do as array dest. And the main thing is to reshape source to the dest, which I think is something that happens. And then copy out would just be an MP. Oh, yeah, we need a copy. And instead of buffer. Now I'm wondering if we need this from buffer. Yeah, we're never going to do this, right? Because we don't do that here. So we can simplify this to something like this. We're going to create a VP empty, right? And then we want to copy that there. And we might do, since these are never going to be buffers, we do as type and reshape then copy out. Copy out, synchronizes after. Let me put that here. Yeah, we schedule a copy to, and then we synchronize. That makes sense. So then by the time this is done, that will be filled. So our dest should be here. Does this, or well, let's try that. Import NLC pi as VP and import numpy as MP. And if we have our VEA is the as array 1, 2, 3. There we go. So if I do mp dot copy the VHB is a numpy as array 0, 0, 0. So they're the same size. And then if I do vp.copy to VHB VEA, yeah, okay, that won't work. But if we do n, then this mp.copy to VHB is now 1, 2, 3. Okay, so we'll do mp copy to dest source, and then we synchronize all these. So if we do that, so I have this buffer object has no attribute buff. It doesn't have an attribute buff because yeah, it is quite clean. We'll see if it's only clean if it works. Otherwise, it's just fake code, like fake news. It wants a buff. Buff comes from what? In ops GPU, create the buffer. What creates the buffer in device? Ops VE. Size should be none. Sequence or int. That's an interesting. Size should be none. Sequence or int. They give me a size that's not an int? Or is it this thing that we want to do? with Python. Okay, so now we're good. Okay, so that always gets me. I really don't like that one. So copy 2 must be an ND array, not memory view. Look at the CPU version again. Okay, so let's copy 2. Do these have to be memory views? I thought we were in charge of what these were, like as buffer is what that was, but I guess not. Let's get these back in here. Okay, so copy in. We can do numpy from buffer source just dtype. So assuming that source is a buffer, get that. Now we have a numpy thing, which we copy to the VE and we synchronize. That's done. Copy out should be np copy 2. Now we get a CPU thing. Dest, which is ND array, and then this source is a memory view. Or do I have it backwards? Dest is a memory view, and source is an ND array, and copy out. Okay, so we have our vector engine ND array, and we're going to copy it to, copy in dest is a ND array. And the source is a memory view. Then copy out should do a memory view from a VP array. From buffer. Just source.dtype, reshape. That was too many clicks. Why does that work? It does work, so that's good. And then if we start training with it, we're getting a bunch of copy ins. And training is happening. So I think that's a good sign. We can stop celebrating all the time. Okay. Now the main, so we are training now. And look at our usage. And slow as molasses. But that's normal. Now, one thing. So how is it that we can get rid of this without taking up a ton of memory? I remember back in the day, you used to have to care about that stuff. Is there a smaller thing that we can start with? I mean, like, how do you get smaller than MNIST? It's just small. It's a small thing. Where's our examples here? Examples. Beautiful MNIST. Not sure there's anything smaller than that. Serious MNIST. What's serious MNIST? Oh, it's like a real MNIST. I see. Simple conf. No. Batch one. Yeah, 89 gigabytes is what it will do. Mixtral, which I don't think I have the memory for. Safari 10. Safari 10 is bigger, but like, so the main thing is if you take 60,000 things, right? Which are 28 by 28, right? And each one's taking 4 bytes memory, something along those lines, in batches of 512. You get 96 gigabytes, right? So like Trio was saying earlier. So what you want to do is not have batches of 512. For example, have batches of 8. Should be fine. And yeah, it's weird because it's been a while since I had to do MNIST with batches of 8. That's seems like it's there's a little room for what's it called, optimization there. Also, we are not doing anything with VP here. So for example, let's go look at our MP dots. This should be able to be vector engineable. EXP2. I hate this so much. Okay, so these I do think should be implemented in NLC Pi. Why? Okay, we have our view. We don't need to deal with that. NP node, logical node, I think that could be implemented on there. Instead of MP maximum, we can have BP maximum. Compare less than, I think we had some issues with that. We might get back to that. Add should be something we can do on the vector engine. Subtract as well. Divide as well. We have multiply, which also should be vector engineable. XOR, not so sure about. But we'll give it a shot. Square root for sure. Sum calling dot sum should be fine. Max calling dot max should be fine. As strided was issues pad is not implemented. Expand to I do think was, so I put that as VP. And I can't remember if there was an VP where. There might be. Let's see. Okay, let's give this a shot. What's your problem now? NP. Okay, let's try that. Let's know how to get it. Okay, whatever. Let's not deal with that. Hey, where am I missing a comment in the cast? Oh, god damn it. That makes sense. Let's see how many more of those I have. Not many. D-type uint8 is not supported, unfortunately. It would be great, right? Like when logically that this would be something that would automatically get wrapped, but I don't think it is, so gotta deal with it. And this is being called somewhere. I think it's in the broadcast too. I mean, kind of need to broadcast a lot, right? Okay, so that's not working. So let's make this a broadcast to what was broadcast to signature. So I can make a function out of it. Yeah, and then search here for broadcast to array shape sub OK equals false. Okay, so let's go back here. Let's make a broadcast to function. And then if array.dtype is equal to np.uint8, then we return np.broadcast to array shape sub OK. And then else we return bp.broadcast to array shape sub OK. See how that works. What did I do? Oh, I forgot a comment. Crazy. Okay. So now we're running. And running mostly on the vector engine now. So that's pretty cool. Not very fast, as you can imagine, because our batch size is quite small. We're using 45% of the memory right now, so in theory, we can go up to 16. See how well that works. I have a feeling this is actually faster than the CPU already, because we're training in 2 minutes. Yeah, it's doing a lot of freeing. Still 45%. I think we can actually go higher. Let's do 128, see how we're doing. Ah. Train step. Test accuracy. This is the thing that's interesting. VE at 128, so let's do 64. Let's get rid of this thing because we just want to see it fast. That's interesting. It seems to be much slower now with a bigger sample. Okay, so we're getting about 4 minutes, 4 iterations a second. We were getting before 16 seconds per iteration. That's 4. That's significant. Does that make sense? 64. Seems like a little off, right? Like 16. Or it should be like 8, right? A little weird. Yeah, we're totally training on Vector Engine, making it useful, so it's not a useless card. I mean, it's not a useless card, but if you're an AI company and you don't use TensorFlow, and TensorFlow is the only thing that it supports, then it's not too useful. And it's training 70 epochs, about 3 minutes. Let's see what we get on a CPU with the same kind of parameters. About 1 minute, so a little ways to go still. That's interesting how this get test accuracy thing. Argmax. Why is that a problem? Is this still a thing? Let me check this tiny JIT thing. Is this still a thing? We got 1 minute to train. And then if we go VE equals 1, four minutes to train. Yeah, about 4 minutes of training, which is interesting. Memory is getting like, going really high and getting really freed. It's not really ideal because you're just going to use it anyway, right? So like you want to reuse your buffers. Does this cause an out of memory error if we don't free stuff? All right, yeah, that's true. The einsum. So yeah, the CPU is using einsum. So if we really wanted to do an apples to apples, it looks like this free doesn't do anything. So let's just get rid of that. Let's go to ops CPU, and let's get rid of its einsum. Now, when we run CPU, we are seeing that it's significantly slower, possibly 15 minutes. Possible. Yeah, about 15 minutes. So yeah, we're faster. Yeah, that makes sense. Yeah, let's see the code that it is producing. I think to do that, you do debug equals 2. And if we run that, we can see stuff. Cool, it's showing you the gigaflops. What if we do that with the VE? What happens there? Just give ourselves a little more space. It's launching a lot of kernels that are kind of unnecessary. So yeah, this should be like doable in seconds, like 1 second, given this size of thing and the amount of hardware we have. Let's also let's run VE test, make sure I'm getting these things correct. Let's get rid of these synchronizing things real quick. Seems to be the same. Okay, what about 4? Yeah, how do we see that? Let's see if we can do clang. I don't think we can. Right? Do like clang equals 1. I don't have clang. If I enable dev toolset 11, do I have clang? I still don't have clang. Yeah, let's look at that output. Where is the output? debug equals 2. File name. Let's go to ops client line 14. Right. Output file.name. And we're doing temp. That's probably dying as we output, so we'll output that and then import red thread.sleep forever. What? There we go. Threading does not have sleep. I do sleep in Python. I could have sworn it's thread.sleep. Oh, time sleep, yeah. Damn it. Time sleep. Report time. Okay, so now we can look at this file. And it's empty. It's empty because we need to write to it. That's the output file name. We don't care about the output file name. We want the program. So let's just print that. PRG. So remember how to click bin. Cancel that. Okay, and let's do that again. That's a very simple program. Not really what I was expecting. What happens if we just put NCC? Now the header is this thing. Right, so this is simple thing. Or at least I think it is. Let's try. Yeah, it's a super simple thing. If we do NCC, or 3, what happens then? We do, it's trying to DL open and stuff like that. It's being fancy. Which makes sense. We can totally do this in a similar style with AVEO or Vita. I think this has to be opt NEC VE bin NCC. Is this doing C++ or? Or C? Can't DL open that thing. But can't check the output. Hmm. Hmm. Doing a whole Vita thing might take a while. That's interesting. Now, I wonder. If we enable that and go back to the VE one. Yeah, they're just doing everything on the CPU, which is decent. So if we look at everything that is happening there, I'm trying S. Why does it say sadly? There's nothing sad about that. Is Copilot like trying to tell me something about my programming skills? Yeah, so here you can see that for this specific training, there's only these many kernels that need to be run. And writing all that out would be a pain in the ass. But we can ask ChatGPT to implement those. Find some. Yeah, so this sometimes works. That's dumb. That's dumb. I need to be more specific. Delete that. Okay, so I want the function to take function to have the signature. Def my find sum S A B. There we go. How's that? Let's make OpenAI work for us. Ah, yeah, thanks for moving me to the right. That makes sense. A lot of the output is on the left. No, I mean, yes, but no, that's too general. It's too general, but is it good enough? We're doing that. take our shape, reshape, we perform the multiplication. How well does this work? I don't think it will. But it may be worth a try. So if we have my einsum here, then we're doing reshapes, which would be vector engines. Those would work. We call sum, which would be vector engines. There's nothing NumPy specific there. How well does that work? Probably won't work at all. Unexpected keyword argument optimize. Yes, we have that. That's the thing. Let's optimize. Yes, we're optimizing. This is the first time that I've gotten code from GPT-4 where I'd be like, touche. Touche. It's not significantly faster, but the fact that it's not dying is interesting. The loss is going up. It's going down. Okay, so interesting. Yeah, there's no guarantee that it's calculating the right thing, given all this stuff. The fact that it doesn't die is quite interesting. But it makes sense, right? We take the things, we reshape them, we do the multiplication, and then we reshape this result and return it. So yeah, that does, in general, it makes sense. Of course, it doesn't have an optimize, right? So it's not significantly faster, though still quite impressive that it didn't die. Let's check. So we were getting, just before it died, 1.10 loss. What are we getting here? Yeah, so the loss being in a similar ballpark is quite interesting. And we'd have to see, like, finish the training and kind of see. I don't think we need to wait so long. Let's change that test to only do 10 epochs. 10 epochs for less than 1 in the loss. It's still going down. 15 or 20 at most. what does the sync to VE thing do normally? So essentially, what it's trying to do is send a bunch of commands to the VE in a batch, and then when you print it out, then it then synchronizes on copying it to the CPU. So essentially, as you're telling the VE to do stuff, it doesn't actually have the results in the next line, right? Like the VE starts working on it, and it just keeps going. And everything that you do to your NumPy arrays gets enqueued into a buffer, and then it will all get eventually worked on. And by doing it that way, you don't have to wait for the data to be copied to the VE and then copied back to the CPU and then copied back to the VE to do the thing and then copied back to the CPU. So that's the idea. Okay, in terms of the accuracy, I would say we can probably leave this at 20. Kind of like maybe 35. Let's just do 35. Okay, so let's go back to the thing. Where is it? Examples, beautiful MNIST. Let's train for 30 epochs. That's good enough. And then let's do this on $30 is equal to 29. That will get us the last one, I think. Okay. Yeah, much better. We only have to wait, like a minute or 2 minutes, which is much easier to do. We can actually see the accuracy of the test set near the end of the training. And then we can compare that with GPT-4's einsum function. Still kind of like that's pretty ridiculous that it would get this and it would get it on the first try. You have to like do some tests to see if it's actually reasonable. The reason why this works though is because if you look at what are the einsums we're doing, they're all pretty simple, right? Like it's the same pattern. You got A's and B's, and then we get one C, result. So yeah, because what we're generating is pretty simple, it's possible to just make a kind of a hard-coded type of thing there. And that would be impressive. I mean, if it's actually like good. Yeah, it's nuts that we get on the first try. Yeah. Anyway, let's see. Our loss is pretty low, so let's see what the accuracy we get is on the VE. Another question. So is there a manual control of the sync to also prevent it? And yeah, there's I mean, I'm not sure preventing it is possible. So in the lazy evaluation, you can kind of see what it's doing. It's like stacking the requests, and then you can flush. So you can choose when to flush your requests to get the results, right? So in that sense, you do have control. You can either flush every time, which is what this does, or do 2 or 3 and then flush it because you know you need the extra memory or something like that. Yeah, or timing wise, you know that it'll just be better. So yeah, they have some things there that makes it pretty nice. Out of memory, damn. That's annoying. It's unfortunate. Test accuracy. And get text test accuracy, which returns the mean of that times 100. Yeah, the accuracy, like because we were kind of striding the max memory when this was 32, then the fact that the training data was still in memory and we're trying to add the test data in memory made it go over. Oh, that's a good point. X test is also big. I think it's 10,000, isn't it? Should be about 10,000, which is quite big. Get test accuracy. What we want to do here I'm not sure how to make mini batches. We need to make mini batches of X test. We have the source code, so let's find out mini batch. Mini batch. Batch size. It seems a little bit like more reasonable, actually. What are we? How are we doing in the memory? Probably not so great. Yeah, we're dead. Let's do that benchmark with our find some in place. But let me get rid of that printing thing. It's useful to know if something crashes, then it's good to know which thing caused it, so we can, like, do something else. But yeah, it seems pretty good. Okay, the efficient net benchmark is good. Benchmark train efficient net. Yeah, and so it's like doing things with a reasonable batch size of 8. So that's why it kind of makes sense. Yeah, it's nowhere near where we should be in terms of the gigaflops. Given that we have 5-ish at our disposal. The fact that we're at, the fact that we have 5,000 gigaflops at our disposal, the fact that we're at 1.5 is not ideal. But this is also small data, so we don't. That can be a thing. Okay, and Oh, you have a great idea. I'm afraid to ask. What is your great idea? It does support JIT operations. So if we can get the source code and then compile it with the thing, yeah. Yes, it does. So Paul, as always, has a good idea. You can do something very interesting, which is user's guide, usage, execution. Where was that? NEC Pi. So there is just-in-time compilation where you can do this. You provide the code for a C function, and then you can get that and run it. So if we can get somehow get that's not so great. So if we can somehow get the code that this is generating, compile it and then call it every time. Could be a thing. Let's copy, paste, rename to ops VEJIT for just-in-time compilation. Yeah, go ahead, join me on the stream. Where does it get this program from, though? Compile. Yeah. Abstractions.
Hey.
Hey, how's it going?
Yeah, I mean, I'm not getting any more healthy, but I thought it's easier to talk about this together. So what I think we can do is, you see that, so the way how I believe it will work is that we can call in compile clang, we can do something with it, as in do the VEJIT thing. And instead of returning bytes, we may just return, like the name of the thing or something.
Yeah, we return this as bytes. If it's necessary to be bytes, we just return that.
I'm not exactly sure whether we need to, but we return VELib.
Yeah.
Like we could do that, I think. And then when we need to call it, we can, do the, as we have this self-name and lib.
Yeah.
We can probably do something with it that way. So, because like we get the header and the program from the renderer, which is the C-style renderer that is there. And yeah, I guess VELib get function should be. That's probably kind of the. Oh, not even sure biggest thing or not. I guess we will need the header because it's kind of using some things.
Okay, so essentially we have this code. Can't rectangle select crappy non-Emacsy thing. Okay, so we have our code like this, and our VELib like that. Does that seem? There we go. Now we go. Okay, so we have our VELib, and if we return that, the code is not this. What was the name of the function, though?
I don't remember. It's probably very far away now.
Syntax. How does it know what? It gets past the name of the function.
No, I think that is the name of the file, or is it not?
No, the file is...
No, that is a new temporary file. But yeah, it does get the function there.
Yeah, we write the bytes of the output here to a new temporary file. Then we...
Okay. Then I guess it's actually easier for us because we don't care. We just, as the code, we put header plus PRG and that's it.
Simple enough. Then
remove the at disk cache there because we are not going to cache that.
Where does that come from? That's weird. Oh. Okay, so compile. Let's call this something different just to make things easier. Compile VELib.
Yeah.
Compile VELib. And playing program, let's change that to VE program.
So let's see. When compiled, when it calls to program, it will call the renderer, and that will produce a source and runtime arguments. And then we will use the compiled strunner.
Not sure if that matters, but let's do that and get a function from the name.
Oh, if debug is bigger than 4, it will print the thing.
Oh, okay. Then we can see that in action later. Now the problem is we need the args and return type. We don't know what those are going to be.
Yes, we don't know what this is going to be until we actually call the thing.
Yeah, I think we can make a little map function there. And then the call. That's once an equal root.
Yeah, I think so. The CPU time execution is probably it's like one of the helpers, so we can probably get rid of that.
Yeah.
So no need for a lambda and no need for the enable. And I guess with that we could even do maybe a print on the buff send files.
And buffs like that, and then print vowels. Buffer syntax and script. Program the JIT device. I think it needs to be like that. This is called the JIT, so this needs to be all uppercase. The JIT equals 1. NEC pi is not defined. Makes sense.
All right.
Okay, I saw some weird ASCII art. Oh, that's pretty cool.
Neat. Store
Float, restrict data 0, data 1, turns void. Okay, so if we can just assume that return type is going to be void. Hopefully VE types has a void. We'll find out.
Invalid number of.
So
that is on call.
Yeah.
Because we have 4 things here and we only actually give it 2. So instead of doing that, we do have this Tinygrad device C microbyte array 4, C ubyte array 4. So can we maybe do on a buffs a thing that is kind of a I think it's not
okay, yeah, we could totally do that. Hold on. It's like because they're pointers.
Yeah.
Right? So these are float pointers. So the actual type is that. I'm not sure if that works. I have to look at the VE types later. But essentially, what we can do is just boot self.velib equal to lib, and we move this to the call.
Yeah, exactly. I mean, that is probably suboptimal.
Maybe. I'm not 100% sure per se.
We don't have the name here anymore.
Okay. Self.name.
But that means that we can kind of do that on the first call.
Yeah. And then we don't have to look it up every single time.
Yeah. But first, let's...
if self.fxn is none, and self.fxn is that, and then we call that like that, and then we had this thing, right? So what we want to do, you might array for.
Yeah, can we
let's look at the VE types.
Yeah, you probably want to look at the device types or something like that.
You mean these ones? Or
Yeah, so we probably want to do a mapping from the Tinygrad type to
yeah,
to those types. Let's scroll down.
okay.
Yeah.
So we have void p. Can I just make it void p every time? I guess maybe not.
I guess you could make everything a void p, but then it won't find things.
Wait a second. This is a double pointer. It says VE types UN64. So I'm assuming it's going to always be
I guess
pointers.
it can be.
So
I guess you can make it void p for everything, maybe.
Yeah.
And then just.
Does it have to be a tuple?
Probably.
Or X in buffs. And I can make a tuple of that.
You don't need to have the what's its name? The brackets around it. Then it can turn its generator into tuple directly, I think.
Okay. See how that works. The program has now attribute fxn. What did I do?
If self fxn is none, and it's like there is no self fxn, so you probably need in init to set self.fxn to none.
Makes sense. There we go. The lid is not defined.
Yeah, because you're not self.
And an integer is required. Okay, so we're getting somewhere.
Yeah, I think.
Is that the first? No.
Yeah, that is the first thing. Okay, so it is happening. Stop. Don't scroll all the way to the top. So what we do get, it is a thing in NLC Pi. Yeah, so it is converting whatever we get into. Well, it is trying to convert something. However, it has gotten a. Now, now your face is in front of the thing that's important. What's the X there? Okay, so F is the conversion, and X is this. And we kind of need to pass the correct thing there. Can you do also a print on the function?
Interesting. So we need to do VE adder for the things.
Oh, we might also need like an allocator thing for this.
Yeah.
Because right now it's using the malloc allocator, and we don't want to use the malloc allocator. What we want to use is the
our allocator.
Is our allocator that we already have created in the other thing. Let's do that and see what happens.
Ops CE import allocator. Assuming I got the correct syntax. Right, and then that's mean, it's not going to work, but close enough. Then
missing one required positional argument size. I mean, the last one is always something bogus. So we're looking at the one before that. Alloc missing one required positional. That doesn't. Do we need a different allocator when we're using that kind of thing? I guess we do, but why?
because opaque. So opaque is not none. Or no, it's because we're calling alloc. Type. Locator alloc. What? So one thing I did notice is the allocator in here. They had another one. What was it in GPU? Alloc image. I was kind of wondering about that, and then I saw here image D type. Let's print that out. See what's going on. Device pi, right? Okay, print type is type.
I really think that it's something different. Like the buffer thing kinda seems buffer thing kind of seems what's the word that I'm looking for? Like red herring. Because it always comes up, even if you are missing a comma somewhere. It's like a syntax error. So I think it's another thing. That
it could be that we're returning something that doesn't have the thing.
So let's go back to the thing that we are kind of touching. Maybe get the allocator copied in here so we can modify it. Okay, we don't need the VE device here.
Let's change this up. The jet allocator.
You can remove the device class.
VE device.
Okay. So is copy in kind of too far indented? Doesn't matter, but
yeah, probably doesn't. weird that it was indented where it was. Okay, last thing we do, it's not anywhere in the allocator, which is interesting.
Name allocator is not defined.
Oh, this makes sense.
Okay. Name VP not defined.
It's VP, and then we probably also need an import. If I is NEP. Okay, now we're back to that. We are not allocating anything.
Alloc is missing one required positional argument size. Oh, I see. Go to the allocator, please. So it's trying to call alloc, I think. But because it is missing size,
that should not help. But yeah, everything is 1 kilobyte, no matter what you allocate. Yeah, I think that's it. It's trying to D-type, which D-types were like float, right? If is instance.
Yeah, let's see what the malloc allocator actually
that's good. Yeah.
does. Because so it does have the underscore alloc as buffer copy in, copy out. It has LRU allocator, which has alloc freeze. So the malloc allocator is based on top of the LRU allocator, which has alloc free cache, free stuff like that. So we have there are kind of several things. But alloc always takes a size. So that would mean, I mean, we could, I guess,
do we need a def2 buffer?
We don't necessarily need one.
Or as buffer?
I mean, because we don't. What about, like, maybe we are doing it the wrong way around. The malloc allocator will already allocate things. Can we get the pointer?
C types mem move.
It's like, let's use the malloc allocator and the buffers that we get, given that we would use. No. Okay, no. I remember now. It allocates stuff on the CPU. We need to move stuff from the CPU to the vector engine. and it was kind of
We are. Okay, so we're in here. Allocator, alloc. And this thing here.
okay.
What is this?
Okay, so
Nice allocator.
if an allocator has S buffer,
Mhm.
let's see.
Yeah,
Yeah,
I think
okay,
we
on buffer.
don't want it.
It has, so a buffer has from CPU and to CPU.
Mhm.
If it has S buffer, it will use numpy from buffer to use S buffer from this. But I think we don't want to have that.
Yeah.
Instead, it will create an empty numpy array, and it will use copy out on it. So let's try to understand what exactly it is that it is failing on, because this buffer object has no attribute thing is, I think, a lie.
Yeah. Here's schedule. Okay, so we're calling run schedule, which calls this
Can you show more of the error again? Okay, so we run this. We see that it has this bunch of stuff. And then we have allocs missing one required positional argument size, which means D type is none. That doesn't make sense, does it?
Yeah.
Because
so what we
D
have,
type is float here. Size
Yeah.
is 1.
size
if
times
opaque
4.
is not none. Else like, I have no idea how this construct can ever fail in that way.
Else.
Okay, so opaque is none. Because all the others before were opaque, right?
Yeah.
Okay. So opaque is none. Now it is calling self-allocator. Can you print self-allocator before this? And yeah, also the things that we pass there. So also print the dtype if instance and so on. No, like the entire thing that we have in there.
Oh, like the entire thing.
I just copy. I essentially want to have to see what exactly is being called. Yeah, that's good enough. Okay.
Alloc 4. That looks like a fucking size to me. I don't know. What in the world? Alloc is missing.
Let's take a look at our VEJIT allocator again. So
it's not being called.
No. So that means we are calling the LRU-JIT alloc here, right? LRU.
Yeah, there you go.
And it has the LRU allocator has alloc. Who says that it's unintentional ASMR? Maybe it is.
So what is?
There's just a comment coming in saying debugging unintentional ASMR.
Yeah.
So let's see. Within the alloc, we do have, like, what if we just skip the LRU thing? We don't care about caching those things, like those allocations. So if we make it based on a regular allocator without the LRU. Okay, let's do that and see what happens. I see it now. Do you see it now?
The what?
Go back to where we define things. There we put VEJIT allocator. It was, before that, it was malloc allocator. If you go to the allocators where they are created, you will see a devious little thing. If you scroll down, like show a bit more of the code, malloc allocator is an instance of the underscore malloc allocator class. That means when it's using malloc allocator, it is using that kind of single instance. So what all we need to do is give it the parentheses to create an instance of our thing. And it has been complaining about size not getting a parameter because it has been calling the class, and the first thing that is self. So it has been
Python.
Yeah.
Yeah.
Just yeah.
Okay.
I hate it when people do clever stuff.
I'll get rid of some prints, but I can't remember where they are.
Ba-bam!
Okay.
A lot more stuff happened until it failed. Signal 11.
Okay, so it's been passing willy-nilly shit around. That's
I think
kind
the
of
first
crazy.
thing that we do is we remove the prints that we have put there.
Yeah. Where did I put those prints?
I think in the device thing within buffer. Look for a class buffer. Is it not there? Yeah, it's on in device pi line 64.
I was looking for one thing. Okay, so let's get rid of these because it doesn't matter. Okay. And then the other thing, which I was like, we're passing buffs. We shouldn't be passing buffs. We should be passing buff.be adder for buff in buffs. Vals, I'm not so sure.
We still have no idea what vals actually is.
So it's just empty.
Yeah.
So
I mean, it could be, literal values for something.
Possibly.
Oh, I've got someone at the door. I'll be right back.
NLC pipe for ND array has no VE adder. Let's look at this again. VE ADR. See VE ADR. Buffs. And actually, I think vals is fine. We just, if we're passing like a 4 or something like that, it's 42. Hey, it hasn't crashed yet. Let's see what our VE is doing. Looks like it's doing something. That is cool. This code is not going to be very VE friendly. Could be worse. But anyway, so there. 73 gigaflops. That's a little bit better. Let me see what else. We turn off the debugging. Let's see what we get. Okay, we're still printing out the vals and buffs because they're ND arrays. They're getting printed, and because of that, they're being copied every time to the CPU. So let's not print those anymore since we know what they are. Okay. Now, how bad is this code? You will see very soon. It is amazing that it's running. So there is that. But we need definitely a better renderer. So I think the next step will be the renderer. I only have 8% battery left though. So let's look at the C style language.
So I'm back.
Hey, it works. Like totally, literally running.
Pretty fast even.
And after it's compiled everything, it's yeah, like running.
And I got just some fresh cat litter delivered.
Oh, cool. Now your
It's
cats won't kill
so heavy.
you.
It's like 100 pounds of stones.
Okay, so we're gonna
At
fail
least
on
it doesn't
the
smell.
yeah.
Okay,
That's right.
cool.
So like that all works.
How many iterations per second do we get, or seconds per iteration? At what size?
1.26.
So how long did this one take now?
A minute and 12 seconds, which is better than the 4 minutes of.
So what was
before.
the CPU time?
So CPU. $20 seconds-ish.
Or the same thing.
Yeah. Although, so this is 1.43 iterations per second, right? I think we were getting 1.26. So we were like a little bit faster, just that the ramp up, right? The compiling took a while in the beginning, and that is messing up our
I see.
thing. So our total time is whatever. Test accuracy, whatever.
What if you set debug to 2? Because it should be showing, I think, something. Yeah. Okay, so those are probably the function names.
Mm. I also have to be careful with this VE because it doesn't have its cover, and it runs a little warm.
I see.
I don't know why they took off the cover and never did anything about it. But yeah, I was monitoring it. Should be fine. Like, we're not really pushing it all that much. Split this vertically. Yeah, now it's ramping up, and now it's doing its thing.
I remember that we also did something in Vector. Let me check what I have done there.
And now where it's doing the accuracy test, which is interesting.
How many gigaflops is it showing there? Because it's like we have our faces, right?
It was 0.0.
Oh, okay.
Yeah, I'm not sure that is reporting that.
It may be that we need to have this thing that we removed that is a helper.
Mm-hmm. Yeah, it's kind of like 0 to 0.
Yeah, so there we got it. Average gigaflops.
1 gigaflop. Or 1 teraflop. Or no, 5 point.
Is that right? 5 point.
Totally can't be doing 53 teraflops on a vector engine.
Yeah.
Unless it thinks that it could, I mean, shouldn't be. But
yeah.
Test accuracy 85%. So not bad, like in terms of the fact that this is a total, like, just regular C.
Yeah, we can probably literally like copy the thing, the regular C thing,
Yeah.
and put a few pragmas here and there.
Mm-hmm. Now let me do the train, but without debugging. Let's see what we have there. And of course, the ramp up is going to be the main thing, but that's fine.
I mean, we can do something about that, I think. I think it's possible to get a reference to... Yeah, I think it's possible to get that cached. You just have to, check the documentation.
Notices regarding Git compilation. I'm not sure if we can cache that. Whatever. Video flops according to that. It's not bad. Anyway, yeah, let's look at
pass complex data into VE arguments. It's necessary to transfer data as nlcpy.ng array or nlcpy.vo on stack.
I don't think there's any kind of complex thing being passed. It's all.
No, but we might get around the NumPy transfer stuff.
Possibly. 331 gigaflops with VE-JIT. We do for CPU. What do we get on the CPU?
So transferring buffer data to Vector Engine. Python objects that support the buffer interface can be transferred to VE arguments by using nlcpy.vo.onStack.
Yeah, so we are beating the CPU.
Let me send you the link to this thing. If I can actually get the link. There.
Links. Actually, I need to give my computer some juice because I'm using my dock, which cannot deliver the watts necessary. Thanks, Intel. We can see what's going on there. I think it's forcing itself into low power mode, so now kind of able to charge the battery.
So another thing that we can do is, and that's also on the link that I just sent you, we can customize the compiler options. Because I think the default options are a little bit...
Yeah, I did do the 03. Oh, I mean, yeah, the NLCPy compiler options. Yeah, what are the default NLCPy options?
And you can actually tell it to even lock the compiler output.
Code something C flags, LD flags. Don't think we need that. NP flags. Okay, so that's good to have. Let's do that. Ooh, having ftrace, that would be great. use NLC. I'm not sure if
Yeah,
that
this
would
if
work.
you use something that needs NLC, like if you have that explicitly.
That would be great if it did, I think, in general. Okay, so
But we can, because there is this C-style renderer.
Yeah.
Like there's OpenCL, there's Metal, there's CUDA, IP, WSGL. So we can probably create a variant.
Type return type, pilot output. Let's look at our.
Or I mean, we can also take a look at the output code and see like where would we like to put something.
Yeah, but let me get the standard like flags that we had in Cyclone.
Oh yeah, right. Like I can see
04 is what we want.
Like I can see certainly one thing where we want to put a pragma.
Mm-hmm.
Like render 4 could certainly do with a pragma for
maybe. I mean, yeah, like we'll have to see the output. msched block, we don't have. We want block scheduler. We want report all. Vector packed is good. We didn't use vector packed here. That could have been important. For inline max depth, we don't have that. We probably want. Let's put these two here. Inline functions. No defer inline instantiation. And then inline max depth is 10. Okay, I do not like having long lines. So I'm going to tidy it up.
No OpenMP.
I'm not sure if that's good or bad. Probably better to have OpenMP.
Yeah, let's enable it.
Up level 4. And then how do we log the output?
Do you want to log it to a file, or like you can also log it to just SCG out or SCG?
Was that in here or was that somewhere
else? Yeah, it
is.
If you scroll down a little bit further, probably all the way down, logging the output. Yeah.
Yeah, standard out. It's fine. Okay, let's see how that works.
This is not defined.
It'd be so cool if this was merged. Okay.
Mostly complaining about missing new lines.
Yeah, and can't do anything about that.
You don't have vectdiag on, but yeah, and vectorized loop.
Did I want vector?
Yeah, direct vector
those
2.
two, yeah. Definitely want that. Stop that. There is port all.
And maybe also on code do a plus with a new line.
Okay, so let's do that and format this in a normal human way. Cool. So yeah, we're getting fused multiply adds being done.
Cool.
Vectorized looped, packed loops. So we're getting pacts happening.
I guess we maybe don't need
vector. Let's see if we can still see this. So in general, if it's saying that it's okay, if it's saying that it's a conflict, that's where we could possibly add a pragma, but we'd have to know that it's not actually a conflict.
Yeah. Okay, I guess we maybe don't want it to output all that stuff anymore.
Overhead of loop division is too large. That's something that can happen. Actually, let's print the program out too, because without it, we're gonna have a hard time. So put code goes that, print code, and then code is code.
Yeah, I would probably not print out everything and just see how fast it is now with those options, and then do the printing.
Man, look at this code.
Yeah, I mean, that looks... It does look like something that should be, you know, very...
Yeah. Anyway, yeah, let's do that. Let's get rid of that.
And the lock stream.
Let's get rid of that.
Oh,
nice. Yeah, it just speeds up the compilation if it's not outputting to nothing.
And also debug 0 or so.
Okay, so once it starts, let's see how it goes.
All right, while that is going on, let's try to figure out whether we can get some kind of reference on the thing, so we may be able to cache it.
I have the feeling if because like after a while it gets really fast, right? So it's totally caching it. I'm not sure how.
Yeah, maybe no, I have no idea.
Very cool. We're at, look at how fast that is. CPU is 1.4 iterations per second.
And this is now because our videos are in front of it. I'm kind of wondering whether I should maybe move it to the top.
Yeah, we could. Top right is probably a good placement. Yeah, it went down to like 1 iteration per second, which is pretty good, I think.
Yeah, can we, like, if we can make this now also cached, would be so great.
Yeah, it would be great. And then we kind of want a VEC style language.
I mean, do we even need that anymore?
We should not assume. We should VE prog in.
Oh, yeah.
And see what it says in terms of how our teraflops are doing. Paranoid Prolary says, "Prepare the ship for ludicrous speed." Yes. Let me grab a helmet because I have the feeling we're gonna need it.
I wonder, can I move now that kind of starts moving things around? Can I move our logo? Or is it fixed in the top right corner? I mean, I can also remove it. It's like people are on the stream know that they are watching Express AI live ASMR debugging.
Debugging ASMR. We should start tagging it on debugging ASMR. That would get us a whole different.
Watch two old
audience.
farts talk about Vector Engine code.
Yeah, and I gotta get the deep voice and I know.
You just get a cold.
Yeah, or get a cold. Yeah, that's a good one.
I mean, at least I haven't been entirely useless today. I hope.
Yeah, I was not even going to try the C JIT today.
It feels like it's actually easier than the other one.
The crazy thing
what
is the way this
float
works.
4 thing is. Oh, let's see. What do we get?
We got a vector op ratio of 64%, average vector length 26. So it's shit. It's like bad.
Yeah. Like we get.
Should be able to do better. This will fail, I'm pretty sure. Yeah. So many things. I think this is half floats.
I see. What means has local?
Good question. What does has local mean? Let's try it. Yeah, also fails. Yeah. So probably
can you scroll up just to see what it is failing on? Unexpected keyword. Global size. And that is in our device on exec. So, okay, so we have this kind of buff thing. And there are values.
Oh, that gives me a...
So there is probably something that
do we need to
maybe
sync
it?
You might not need to sync.
Yeah, let's try not syncing.
Anyway, so...
And we can also, another thing that we can probably try rather easily is giving it the malloc allocator. And instead of using buff VE adder, we can use VE on stack. That is also the thing that I've linked here.
Okay, so we can do the malloc allocator. Then here we do buff. What?
It's nlcpi.vo.onstack.
Oh, okay. And then, so VE adder, we do VEO.onStack buff.
Yeah, comma, we kind of need to give it an intent for the thing.
Do we know?
There is an in-out intent, so
Okay. Okay, so pretty much
it
same
is
same
the same
results
thing.
with the sync, 85%. So if we don't need sync, we can probably not do that.
Yeah.
And that's it.
Yeah, let's try that. Let's see whether that works. No. Buffer object has no attribute.
Wait.
Yeah, we need to.
There we go.
Oh. I guess we have a bunch of prints somewhere.
And allocate, yeah. Let me search for size.
Interesting. Do call async stack crossed page boundary. Ah.
Okay.
That is a thing. If we are sending something big that's not on stack, that doesn't fit on the stack.
Was there other thing? Like, can we do on heap or copy on heap or VH pointer?
Yeah, I'm trying to see whether there is something, but I think so. If we have VEO available here, can we? Oh, interesting. Oh, very interesting. Yeah, I'm looking into the PyVEO bindings stuff, and apparently VEO is this PyVEO thing, and it's like its own thing.
Yeah.
I think it's probably better to just go with the one that we had. It's at least for now.
Yeah, we have on stack and we have VE mem pointer. So it is possible to maybe later on optimize that if we have something, but I don't see it happening anytime soon. So let's
but that is a thing that we maybe I look into it after the stream or so, because we could use an LRU allocator.
Yeah, like with the LRU allocator, then
and because we do have the low level allocation methods here.
Yeah.
And it will then reuse the already allocated memory because they did that. I mean, getting this. I mean, this. I'm not sure whether that will work, but I mean, it could.
Yeah, it could. I think if we can switch from the on stack to the VE memory based off of where it is, using the LRU thing, that could speed things up. Which I think there should be room for it, right?
But first we need to kind of figure out how to make the average vector length better.
Yeah, exactly. So right now, like we can look at how much.
Another interesting thing though. Memory used just for gigabytes.
Yeah.
How it should be. I mean, even
Let's,
that is
bring
kind
that
of
up.
a lot.
Let's go back to the thing and bring it back to its original 512. And man, this thing's so slow. It's just like crazy. Okay.
Well, that is also a thing we may want to, maybe comment out just to see how much, like how it is during training.
Well, I mean, in general, like it's 1.1, 1.2 iterations per second in there. Yeah, so we can comment that out. Though it feels like this has to totally be faster than this. Why is this so slow? It makes no sense. Makes no sense.
Right.
Let's see.
It could be that it has this Tinygrad thing, so maybe it is compiling before it is actually doing this thing. That's why it's so slow then.
Question. There's a compiler error if you comment up Tinygrad and you realize there's something weird with int, which is no longer the case because we can comment it out and it's perfectly fine. Let's try that. Yeah, getting this started is serious work, but
yeah, it seems to do something like the first few iterations.
Yep. I'm not sure if 512 is good or not.
I mean, 512 is a big, just a bigger batch size, right?
Yeah. So it is doing more training.
Oh, yeah, true.
Yeah.
But waiting for 20 minutes to see the prog-inf is kind of meh.
Yeah, I don't think 512 will do it. What are we doing on memory? Like, memory is reasonable.
46%.
Okay, now we're down to 16. But yeah, it's been a while since I've like played around with this on an MNIST. Yeah, I remember DL4J like back in the day, like 8, 16, 32. Oh, we got 32, and then now it's like, oh yeah, let's do 10,000 one go,
Yeah.
and we finish training in 0.2 seconds. So I get, like Tinygrad isn't 100% there, or where DL4J was, but that's fine. Like, because this is pretty cool how easy it is to implement this extra stuff.
Yeah.
And we do have the compiler outputs regardless.
Oh yeah, let's take a look at this.
So this is really good for Cindy, right? Like this style of doing things is great for Cindy, and can sometimes be good for the vector engine, but it's like not necessary, and the compiler can probably do a better job if you're not getting in the way of stuff. So, and we can see here that this is vectorized, and this is expanded. So it's not getting in the way per se.
What does it tell us about, if you scroll down below it? So it is a packed loop. Vector load, vector store, quite a lot. It is using all 64 of the vector registers. Interesting. Um,
Is restrict necessary?
I have no idea. What does restrict even mean?
Restrict it to a register, right? Or no, restrict that it's not overlapping. So while not necessary, it's possibly helpful. Now let's move this to 32. Tried this. So we tried a bunch of things. So like there's this we added, got rid of restrict. Probably not ideal.
Yeah. Yeah, I'm looking at the language renderers and what they are doing there. And I'm trying to, I guess, understand.
It is kind of crazy. Or well, not necessarily crazy. It is just as dense. Dense code. C style. The LMVMIR is actually like pretty reasonable looking in terms of like size and stuff. And then the C style is it's a lot.
I'm kind of trying to understand where things are coming from, because it seems like there is the language itself provides some things, and then there is the micro-ops to C style method that is, well, actually not that long. It is about 180. Is it even? No, it's just about 105 lines long. And that is where the more interesting things happen. Like, what is KK? What is SSA? Who hurt you?
So interesting. These, I think there's was exp2 and log2 square root. Those were special. You want to use special stuff for those.
I guess the SSA thing looks kind of like doing something with the cache. And then it's in, and if it's a loop, it is render 4. So that means that the loop, kind of this nested loop thing that we've seen, must be already a nested thing on the Tinygrad level.
That's the wrong place for that kind of stuff. Although, who am I to say? Stormcast
Microops ALU.
How in the world can we do that and also do CUDA in the same way?
Const load I store cast, define local. Define global and gap. What the hell is a gap in GP?
It's very dense code. This, it's like, what uses this micro ops loop? Here, hold on. Let me search for. You have it for somewhere in here, right?
Are you looking for render 4, which is literally just it is in the C style language.
I see. What is doing the packing? Something is doing the packing. Or like, as in something is doing SIMD. Where are we at? UOPS the C style. If metal, let me do the SIMD
Yeah,
group
but that's
stuff.
only on
That's
the
only if
MMA. AMD's WMMA instruction is a direct response to NVIDIA Tensor Cores. So that's, I guess, something related to that. So you look at metal. Yes, it's include
sample functions,
device, SMEM. Yeah, that must happen kind of somewhere early, I guess. Like in whatever is linearizing that stuff. Wait a second. There was a thing. I remember seeing it.
But in general, it looks like it's not too bad.
So the linearizer can get linearizer options.
We don't want. Let me try something. We don't want OpenMP because the code isn't generating OpenMP code.
Oh, that's right.
But we want to see if we can use mParallel, possibly. So let's try that. Yeah, if that makes things 8 times faster, that would be great.
Yeah. I mean, it would still be kind of slower than we'd like it to be, but
yeah. And so for those who do not know, so mParallel is one of the things that you can do in the NCC compiler to generate multi-core code from just a regular for loop. And it will try to do that. And if you don't do that, well, then you want to use OpenMP's pragmas to kind of make your code be multi-core. And the vector engine has 8 or 10 or 16 cores. So if you want to get the max performance out of it, you need to do that. Now, you might notice that when it's running here, there's 8 threads kind of happening, and they're all at 100%. That's not necessarily the case, right? Like they're waiting, they're busy looping on their instructions. So they're always going to look like they're busy, even though they might not actually be busy. Yeah. For a second there, that looked much faster. But yeah, it's always hard to tell if you're like making good use of multiple cores or not with the way this currently is configured. We can also try, I'm pretty sure one of these is an old vector engine. The other one's a new one, if I'm not mistaken. Well, not that new, but like newer.
So,
I should probably get rid of these debugs as well. So I'll be getting ready to push this up so people can look at it. Kind of probably get it ready for a pull request to the official repo. See if Yohat's interested in that.
So what do we get?
Average vector length 9. That's terrible.
Yeah, why?
That's so terrible. And the performance is not like worse, but it's like not all that better, which is kind of weird.
Yeah.
I wonder if something else is going on.
Oh, it could be that NLC Pi is the issue.
It could be.
But given that there is Pi VEO, and we really don't care all that much about NLC Pi, and NLC Pi isn't as free available as Pi VEO, I think, because you need NLC for that.
It would be NLC Pi requires NLC, so it's there.
Yeah, exactly. But Pi VEO does not. So someone who doesn't have NLC could be using that.
Yeah.
And it would allow us to easily cache that stuff. Because it's literally a wrapper around this stuff, along with let me send you a link. I mean, it hasn't been updated in 3 years, apparently, at least according to the releases.
I probably want to look at. Well, yeah, I don't think Pi VEO needs to be updated per se.
And it has an AVIO thing, so
145. It kind of makes sense. This would be 64. Let's get rid of this and do this. Let me try to optimize the batch size for things. That's probably the best way to measure.
So I want to send you the link. So the most interesting thing, I guess, right now would be the VE build. Because we can be like VE build, build SO.
Yeah, the main thing is
and then
this
we can
to
cache
NumPy.
that. Oh, we don't need to NumPy.
You don't need the NumPy?
Yeah, we can use the VO proc alloc mem, free mem, read mem, write mem.
I see.
And that's just pointers. Yeah, and just destination, stuff like that. Things that we already get.
I have to admit, it would make things a lot easier.
No, whether it's a lot easier, but
well,
it could be a thing.
I had to build NLC Pi, and
yeah, I mean that is true.
it like NLC Pi generates, like they have a generator. They take every possible combination of supported NumPy configurations and generates C++ code for each one. So you have 200,000 lines, 200,000 line C files for minimum and maximum and all that stuff. It's intense.
And it also allocates some memory when you start it.
Yeah, that's another thing. Okay, now that we tried bigger, our vector length is 30, which just sucks.
Yeah, we want something that's closer to 256.
128. Just kind of go around these numbers to see which one makes the most sense.
I mean, it always takes quite a bit longer, so you probably want to turn down the range. Like 30 is a lot now.
Yeah, that's true. What we want, see, 30 at 16 and 85. So 10. Probably get 85% at 10 ish. Get rid of these files. So seeing the new ones.
So there is a function called getGroukedDims.
In where?
In linearizer.py. And that goes up to, well, max dims. We might set that either to 1 or 256.
Maybe give that a try. Which folder is that in?
In CodeGAN.
So there's kernel pi, and then there's linearizer, and you get grouped dims, max dim.
So there is.
Set that to 1.
There
No,
are kind of several things that we may be so can you pull up something with code?
with the code, the generated code, you mean?
Yeah. It's mostly to understand. Oh, have you removed the things? Like all those files just now?
Yeah.
Okay, I wasn't watching there.
Let's do that again.
So what you want to look at is linearizer.py line 206.
206.
Yeah, so we have get grouped dims here with GIDX and grouped dims with LIDX. And get group dims takes a prefix, start dimension, local dimension, and max dimension. And I think we may want to look into what we are passing there. Because on the vector engine, we may want to have a lot higher values for this.
Yeah, why is it 3?
And I'm not sure. Do we have has local set to 0 to false?
Yeah.
So its max dimensions is currently 0, I guess.
Yeah.
Let's see what 0 means.
Yeah, what does has local mean? Where is has local? Was true. Nowhere. Vector length is crap.
So I guess we care about the local dimensions then? No. So we do have as the upper limit also this self global dims that we like if we ignore this has local aspect of it, there is self global dims on our linearizer. And that comes from I have no idea where that comes from. Oh, come on, why is it or why isn't it assigned anywhere? Okay, so that comes from kernel then.
Has shared. There's also a has shared. Technically, we do have that. Oh, we can put global max and local max.
Yeah, I have no idea what that is or how it's supposed to be used. The global dims thing comes from the kernel class, and it returns self first reduce minus self local dims.
Device maps allocation.
And okay.
Use on the code gen and padded with ones. Global dims. What? Well, we can try and see what happens, right? So we can set global tins, right? Is that what it was?
Oh, interesting. I just found something very interesting.
Mm-hmm.
In the CodeGen kernel py,
Mm-hmm.
there is a thing called tensor cores, which exists for metal and hip.
Hmm.
I wonder, because you have like thread local sizes, thread local aliases, stuff like that.
I see.
If we can define something for that, for the vector engine.
We could possibly do that. Okay, so if we do jet, why is there two though?
Different sizes. Because it has data type in half and data type in float.
Let's do just float for us. We don't have halves.
Yeah, let's go with just one.
Okay, so VJet device, our dimensions. What are our dimensions? Where is this? What does this cause to happen? Like, what thread structure?
I have no idea.
Let's see. Tensor core. The crazy thing is the metal one, right? Like, let's look at the metal code. Metal matmul py.
So there is apply tensor cores. It's a high level optimizer. And if it is like 4 tensor cores in device, this if use tensor cores and has local and reduce up.
Where is thread?
So it will try to apply a, like it will try, if you have tensor cores, it will try to produce a fused multiply add.
Which we already kind of do. Whereas then if you looked at the...
like for a tensor core in particular.
I see. Let's get the actual code back up here. I think I need to log stream to get the actual stuff. What did I do? What did I do now? Global things. Okay. We get let's get rid of that. Okay, and then with the logging, I think that causes reporting to happen. There is loop, pack loop. Multiple store conflict. Multiple store conflict is the thing that I think, but yeah, you can see fused multiply add operation applied, right?
Yeah.
So we don't necessarily have to do anything special there. The main thing is this multiple store conflict. Or
can we like
in the render 4, we could give it a shot to IV dep every 4. Yeah, it's probably a terrible idea.
I mean, probably.
There's a loop that has the. It's either going to be in the sort or. Like I have the. Just do everything, ignore the math. Okay, CPP Provetis for prefix sum. Vector registers, that's kind of good. Let's do sort. And the crazy thing. IV dep V overtake. And I think there was one more. There's like a What's VOB mean? I forget.
Come again?
There's VOB.
I don't remember.
Yeah, I think these things are what we could do. I think let's just do IV dep.
Yeah.
In the render
That's what
4.
we usually.
Let's try that. Multiple store conflict. Where's my code? Ah, here it is. Okay.
Okay, so it's 1004. File that we're looking for is called 1004_20. So I think you're in the wrong file.
There's a lot of files right now.
Yeah, scroll up all the way to the beginning. And there's none of those files.
Whatever. I'm pretty sure we'll find something. These. So the thing is,
well, this one doesn't have the. So like otherwise the pragma would be there.
Yeah, it's true. Practically. Vector length is more or less the same. And the M flops, which I don't really understand. Anyway, let's delete these things are called what? .l files. And let's run this again. Okay, now we can kind of see what's going on. We have our pragma IV depths. And yeah, so this is what it's talking about. multiple store conflict. And we want it to stop doing this.
Yeah. So we do get
Can I find
we do get
these?
something. I mean, the RIGX stuff is yeah, reduce index. And it's a
It's doing
variable.
this because AVX 512, and it's unnecessary for us. Well, in general.
So it's doing like 4 of them. Where is this 4 coming from?
Yeah, it should be 8. Why is it only unrolling? Unroll. You're unrolling stuff? Is there an unroll thing? Type 12. Unroll is used where? Well, I'm not sure if this unroll is the same unroll we're talking about. Tensor core dims 2. Is there a default tensor core?
So there are. I think not.
Why is there 4? 4 would be 128-bit vectors, right? Yeah.
Yeah, and that is AVX 128 or AVX 2 as it's called.
I see. Casting smash is a reduced and upcast the reduced loop unrolling. No simplify needed since it's Jefferson upcast. Splits in 4. Okay, well, if we put splits in 1, wait, split is used where? Apply opt unroll, right? So if we do that and do that, and then generate this again, or remove all the L's. That did not work.
Maybe applying unroll in.
Okay, so if we do this, we now see 1, 2, which makes sense.
Okay, so if we set that to 1, what was it? I kind of was looking at the other part of the screen.
Yeah, kind of failed. Let's see.
It failed because of?
Assertion error. Shift add 2 of amount 1 or node is meaningless.
Okay, let's look for that and maybe It's in line 406 in kernel.py. Yeah, let's let's just comment out this assertion for now.
Makes you wonder, like opt amount. You can set it to none.
Okay.
Dimensions.
Okay, so let's have the other assert again. Let's re-edit, and instead of going for 2, let's go for something really big. I mean, like, I'm not entirely sure whether 256 is right, but I guess let's try it. Just go ham.
Yeah. That also failed. Can't be more than.
Then let's do 32. Then let's do 32.
Can't upcast more than 8. So this is unrolled. This is upcast. And this bottom one.
I guess it should be the same thing.
That's an interesting thing.
Okay, so at least this like 2 times more this time, right?
Yeah. Well, now we get. Now we're getting that's
tiny
stuff.
thing.
That's trivial
2
stuff. There you go. Looks about the same. Oh. Yeah, it's doing more or less what expected. Hang on a second. So there is a way to disable this, right? That's the thing.
Is there a way to disable unroll?
And coded optimization. Oh, interesting. Yes, ops has local, then it does some stuff. We don't have local, so this is if it's shared and whatever, we don't. Cast float 4.
So the thing that has just finished has an average vector length of 28. Doesn't sound too good.
Yeah. So.
And it is also kind of 2:30 in the morning for you, as far as I can tell. Or almost. Yeah. I think we should end the stream on a cliffhanger.
Possibly fly ops. I just want to know how to disable this thing. By default, this is 4. And if we make this empty,
oh, interesting. Will this work?
Yeah, hold on.
No.
Move
Oh.
the L's and then do that again.
Oh, yeah. Okay. I thought it crashed.
I wanted to see it. Still multiple stores, so there might still be something else.
Yeah, that could be entirely
necessary.
Different.
Yeah. Seems like it's still doing the 4. There might be more unrolls to decode somewhere else. Yeah, that's a big ass problem. Yeah, that's speeding things up. Vector length is still 27. So yeah, I don't think it made a huge difference. But
yeah, I think it's this unrolling is kind of a problem.
local side effects in 32. Yeah, I think that's something we'll have to, like, I don't know, maybe ask a GeoHot about. Because it's kind of assuming, I think, in multiple places that you need to write code like that to be able to get it optimized for computers. The vector engine is not that kind of computer. Why does it say put? Actually, we could comment this unroll thing out completely.
I guess you have to put a
Pass.
a pass there, yeah.
So it's not just the unrolling, there might be something else, but at least some places might be a little bit better.
Yeah. I mean, that seems to move along rather quickly.
Yeah.
Like, I have no it's been so long that I've seen this run that I have no idea what the batch size currently is.
I changed the batch size to 32.
I guess let's run it on CPU.
Vector length
Yeah, the average vector length is worse even now.
is worse, but how in the world? Okay, so I do 1. Okay, so
That's
1.2
1.2 iterations per second.
Yeah.
And we have 1.4 seconds per iteration.
Yeah. And that's without unrolling. So if we enable the unrolling again, wait, where was that in kernel? Okay, so this is 4 and this was 4. So for the CPU, Well, we should probably try something slightly bigger than this one. 1.15, 18, because the thing about this is that it fits in the well, it's like the thing that happens a lot with MNIST is that MNIST happens to fit in the CPU cache,
That's
and then
true.
that's really fast. But let's see. Can we
there's
train...
the benchmark of train efficient net.
Yeah.
I mean, we could try running Llama.
Yeah, that's what I was thinking. Like, can we run one of the bigger things like Llama or Stable Diffusion?
As long as you have the correct weights around.
Where does it get the weights?
Yeah, there you have your example. I think for Llama it should be that I saw it.
The module named
there.
sentence piece.
You will need to download and put the weights into the weights/llama directory, which may need to be created.
Can we do a random one?
Random one? No, I guess you need to have them pre-downloaded.
What kind of weight? Safe tensors.
Single or bin file. No idea. I guess original one?
Yeah. Did we have
like the
ones in this machine?
Probably not.
Yeah.
I think it was a different machine where I downloaded them originally.
Mm-hmm. I have Llama GGUF files. They're not safe tensor ones. What else can we do?
I see that you're on fire, but I think you also need to go to bed.
Yes. This download stuff? It will. Think whisper.I will download stuff. So let's try running it. Python whisper.I. librosa. That's downloading a lot of stuff. But yeah, it's exciting to be able to possibly use these vector engines for deep learning stuff. That would be very cool.
Especially if all the stuff can be, running.
Average vector length 234.
That's pretty good. I mean, it probably didn't do anything, but
no model name TikToking or TikToking.
I mean, what will it even do now?
And audio.
Is there like no requirements TXT?
No, I don't think so.
The joy. Yeah, you're missing part audio. Not real. You're missing the part audio. library.
Let's see if it's available. Yeah, it's fine.
Yeah, it is.
If I can run Whisper on these vector engines, that would be pretty amazing. And install port audio devel. Also, it's been a while since I messed with ALSA. And we need Pi audio, right?
Yeah, we also need to pip install that now. Or try to.
See if it works. Okay. And if we run that, chat said it's not running. It's listening. Okay, so now it's listening for something.
Yeah, it's literally listening to the microphone on this thing.
Yeah.
I think you can give it like a file to work with.
Transcribe file.
Yeah,
But
it's sysargv1. So if you have an MP3 file or something like that, or maybe a WAV file, I have no idea what exactly it expects.
There's some sort of test file out there that we can use, because I don't think I have any.
I mean, I can, or you can literally record something being like, hey, it's Eduardo speaking.
Yeah. Do I have some sort of transcription? LB3.
Oh, the regular Whisper has a JFK.wave. Let's see whether
that's exactly what I'd like to have. Something like that.
Oh yeah. The Whisper.cpp has that also on their thing. I'm going to samples. And
JFK wave. So if we in this, go to raw.
I know you've downloaded that.
We can wget that. Now if we whisper JFK wave. Loaded weights. You're running. Pretty good vector length. If it ran. This is trying to use FP16. Okay, so that is something I'll be like, okay, we can save that for next time. So somewhere we have to do something about ignoring half or making bfloat 16b the way it is. But yeah, very close to having something that is interestingly.
I mean, we could
usable.
just define half as float.
Oh, is that somewhere?
No, that would be like a header thing.
Oh.
Or, but I guess.
Yeah, it wouldn't work.
Why?
The shapes when the data is in 16-bit, right?
Yeah, but when we are copying it to the vector engine, shouldn't it take care of that? So if you just in the ops VE JIT thing, if you scroll up to where we have the header, yeah. If you define, like we have int64 being long, there is define half being underscore underscore fp16. Like,
Oh.
what if we do that just as a float?
That would be interesting.
I mean, I think it's getting a bit further than before.
Yeah.
You said, and
Times
things.
7,
Oh, it's
2, 4.
I guess it is passing a value.
Yeah, what's it? Let's print it out and see. I thought values would work as is, but perhaps we need to wrap them in a NumPy or a.
Maybe probably. Let's see. Okay, so
Bells
right before
2.
that, yeah, bells
Okay.
2. So I guess the archetypes. So what we need to do is in line 32. We also have some additional archetypes. So let me get back to the documentation.
So we have to do the X in buffs, and then can you add 2 tuples?
I think so.
Yes.
Yeah.
Okay. So we just plus, and then we have some sort of.
Yeah, I think we just do the same thing. Put a tuple around it, so it doesn't become like a weird thing. Probably they should have removed the print, but
yeah, it'll be fast if we do.
In any case, if that does work, I guess it's something for another stream.
Yeah, figuring out
if you
how
can
to
push that to like an Express AI repository, I'd like to play with it a little bit off stream too.
Yeah,
probably like
set that up.
I think the first thing that I want to try is to set up the what's its name? PyVO instead of using NLC Pi for that.
VE Tinygrad in Express AI.
Okay. So is it getting further, or am I just impatient?
One of the two. Not sure.
It feels like it's producing the same thing over and over again.
Possibly. Lots of exclamation points, at least.
Yeah, cool. So what's the average length? 107. Could be better.
So bad. Was the exclamation points the output? Who knows? Find out next time. on the Express AI podcast. Yeah.
On the Express AI ASMR debugging
Yeah.
channel.
Okay, cool. So, yeah, 3 a.m. is about the time I usually go to bed. So I'm going to sign off now. I will push what we have so far. Let's clean up things a little bit. We don't want to change that. V-test, we don't really care about. Extras, yeah. I didn't really understand how to get examples extras to work, so I kind of copied it around. So let's get rid of that. This is also unnecessary, I think. So RMD init line examples. And this is...
I think you should have removed it from extra. Because now it's like it removes if they remove the init from examples.
Let's revert that. So that. GMM, let's see. I didn't change this. Okay. Device pi. We have something in here that we changed. I don't think so. We did. Yes. Okay. So in device pi, I added V, so definitely need that. Device pi, I thought I got rid of those print statements. I need this. We don't need that. We changed, we added VE in there. That's good. Okay, seems about right. Let's stage that. C style.
I
not
think
sure
the pragma wasn't necessary there.
Yeah. I think that's the only thing we have in C style. Yeah.
Yeah.
This, we'll skip the clang. I can revert that because we don't want to add to clang. Ops VE and Ops VE JIT are the things that we want. And yeah. We add support for the NEC Vector Engine. Let's go ahead and push that.
Oh, hey, we've actually got another question in here from Annual and some number. What do you think of the Mojo language? I haven't even heard of it.
Mojo as in like the modular Mojo?
The programming language for all AI developers.
Yeah.
I guess I don't hang around on Hacker News enough.
Yeah, so the thing I don't like about it is I can't install it. So don't care.
It kind of looks like typed Python.
Yeah. It's, quite interesting, I think. But since they don't think that Intel Macs are a thing, they can go screw themselves. Git status, git note, add.
Scala C++. Like, kind of dishonest on the speed up there. Oh yeah, if we do just linear, that's what scalar C++ means. If you just do linear C++, then things are faster in Mojo. It's like, yeah, put a OpenMP SIMD or OpenMP parallel on things, and then the C++ is also going to use the entire hardware.
So, upstream 2, and then get push upstream 2 master. Why is it rejected? Because I gotta fetch it, get fetch upstream 2 master, and then push. Fast forward. Why is it not?
So then there's follow-up question. What about the Julia language?
Julia is pretty nice. And
I mean,
I think there's the branch for it too.
Yeah, it's like if I had to learn, like if I had to decide whether I want to learn R, MATLAB, or Julia, I would certainly go for Julia these days. Back in the day, I learned R instead of MATLAB because it was more available, more widely available than MATLAB itself, as in free. But yeah.
Okay,
Julia
so
is kind of nice.
So I think I have pushed something somewhere. I want to push.
Yeah, I don't see it yet.
Yeah, this is wrong. I'm going to push. Stream 2. And how do I tell it to push and get remote? I have upstream and upstream 2, and I want to push. Yep, push master upstream 2. Master is now a Git repository.
And I just put upstream 2. Haven't had to use that, from the command line in a long time.
I know what it is. There's a commit from
1 hour ago.
1 hour ago. That's why. So I need to git rebase upstream to master.
Unstate changes.
Mustache. Rebase updated that. Now I can push to upstream 2.
Yeah.
Okay. Now
it's there. Add support
Added
for
support.
NEC
Yeah.
Vector Engine.
Okay. Cool. Why it's not verified, I do not know. Why is it not verified? Did my GPG key expire? That could be it.
No, I think it like my keys, my commits when I push them like that also tend to be not verified.
I need to fix that. But anyway, I will share this with people, and the people who happen to have vector engines and all the necessary stuff, you can give it a try. needed a lot of monkey patching, but mainly because Tinygrad requires Python 3.9 and NLC Pi does not support Python 3.9. It only supports Python 3.8, so you have to build it. And because of how big it is, it takes a long time to build, and it crashes the compiler a lot. I had to like restart the build like 30 times or so. So after like 2 hours, it finally built NLC Pi. So yeah, not ideal, but people can give that a try. And yeah, I will see you again next week. And until then, come join us in the Discord, ExpressAI Discord, or email us at hello@ExpressAI. Yeah, we're waiting. So see you guys later.
Yeah. Bye-bye.
Bye.